Alright, so today we're going to learn about 6.1, which is all about light waves. So there are three characteristics of light waves: wavelength, frequency, and amplitude. So wavelength is the distance between two consecutive crests or troughs. So a crest is basically the distance from the 0 point to the highest point of the wave, and a trough is the distance from the 0 to the lowest point of the wave. Wavelengths are typically measured in meters or nanometers, and are represented by the Greek symbol lambda. So frequency is how many wave cycles pass through a given point through a given period of time. And it's measured in hertz, which is basically how many wave cycles per second. And frequency is described by the Greek letter nu. So amplitude is the distance from the 0 point to either the highest point or the lowest point. For example, if this was 0 and the height here would be 4 and the height here would be -4, the amplitude would be 4 because the distance from the 0 point to the top point is 4, while the distance from 0 to the bottom point is 4. Amplitude cannot be negative, so basically the absolute value of the distance between the middle and the highest or lowest point.
Alright, now that we have these characteristics of a light wave, we can use them to calculate, use the ones we have, the given information from these characteristics to calculate missing information. For example, we have our first equation here, C equals wavelength times frequency. And this equation you can use to solve missing wavelength or missing frequency using this constant c, which is the speed of light constant, which is 2.998 times 10 to the 8th meters per second. And using this constant, when we solve for either wavelength or frequency, we have to keep either of those in specific units. So wavelength has to be kept in meters for this, it's a pretty bad drawing, this certain equation, so this has to be in meters. So you have to convert usually from nanometers. And V is always kept in hertz. So, as you can see by the equation, you can see that wavelength and frequency are inversely proportional to each other, as if you solve for either one, you get V equals C over wavelength, or wavelength equals C over frequency. Scientists have found an equation to be able to calculate the energy that a light wave produces, and that equation is energy equals H, which is Planck's constant, times V, which is the frequency of the wave. Now, this is Planck's constant right here, 6.626 times 10 to the negative 34 joules times seconds. And this constant times frequency, which is always in per second, will cancel out these seconds and give you the energy of the light wave in joules. Now, energy and frequency are directly proportional, as you can see by this equation, with this being here and this being here, and you have the constant multiplied by the frequency. So as the frequency of any light wave increases, you will have more energy from that light wave in joules.
So atomic spectra is used to identify elements in a sample. So what scientists do is they use a spectrometer to put light through a prism, and they get these lines as a result, and these lines show different energy levels for the elements. So as you can see, there are multiple lines for certain wavelengths for certain elements. So say we have an unknown sample here, we have 5 different possibilities. We can use the atomic spectrum to discover what sample this is by just comparing the lines. So we can see here that strontium is basically the unknown sample. So lines are also finite, meaning that there are only a certain amount of them, and they don't continue forever. And also wavelength of photons are also unique, meaning that there are not two wavelengths for two lines for a single wavelength. As you can see here is one line for every single wavelength the element has, but there's not two lines at the same point. This is a picture of the electromagnetic spectrum. As you can see, we as humans can only see a small portion of the whole spectrum. As Brennan mentioned previously, wavelength and energy have an inverse relationship. As wavelength decreases, energy increases, but as wavelength increases, energy decreases. Isaac Newton showed that there are many different colors in one ray of visible light, and an atomic spectrum used to observe this. An atomic spectrum shows a wavelength at which light is emitted by excited electrons in an atom, and is created by using a spectrometer to capture light beams. Each element has its own unique spectrum, making it a good way to identify elements. In the image shown, we can compare the unknown sample to other element and determine that it is strontium, based on the lines. Photons are produced when an electron moves from one energy level to another. There only are a certain number of them, and each one is different. Now we're going to do some practice problems. So the first question asks to find the wavelength of the light in meters if 2,550 wave cycles pass their point in 5 seconds. So first we need to convert the wave cycles per 5 seconds into hertz. So we just divide 2,550 by 5 and get 510 hertz. Next, we use the speed of light constant and the formula to find out what is a wavelength. And we find out that it is 5.9 times 10 to the 5th meters. So the second question asks what is the energy of a photon with a wavelength of 100 meters. So there are 2 steps to this problem. First, we define a frequency using the speed of light constant. We divide the wavelength by the speed of light constant, and through that we get 3.336 times 10 to the negative 7 hertz. After we get this number, we can use the Planck's constant and its formula to determine the energy of a photon. So what we do is we multiply the frequency by the Planck's constant, and we get 2.21 times 10 to the negative 40 joules.